Okay, lesson 17, parallel plates. So what we're dealing with these parallel plates here, you can see like in our picture, we've got a battery. And then, on the negative terminal of your battery, we've got that attached to a plate. So these are going to be parallel plates that we have going on here. So there's one plate, and then there's the other plate on the other side. And thinking just in terms of like electrostatics, right? About like electrons moving. This makes sense the way this is set up, by the way, too, right? Is that the electrons would want to move this way, right, down the wire and collect on this plate, and the electrons would leave this plate, right, making this end positive. So that's what's kind of happening there. And what's happening because we're doing that, we have a bunch of electrons on this plate, a bunch of protons left on that plate. There's a difference between them. Those things are attracted. And when they're attracted, they end up making an electric field, right? Because just of that difference between the electrons and the protons on either side of there. The idea with plates is that the field strength in this case is going to be the exact same everywhere. So the field strength will be the same at every point on this graph. It doesn't matter where it's at. So the field strength will be the same there. Okay. Here's an example of the way that looks. Now, new formula is this one. So we got the electric field strength is going to be E is equal to V over D, where V is the voltage and D is the distance between the plates. So now just careful on that, because sometimes the question will say, maybe that the distance from here to here was like, 10 centimeters or something. So that would be my distance between the plates. But it might also say in the question that, some object is like, 3 centimeters from one plate. You need to know that the distance in this equation is the distance between the plates, not the distance from like the object to the plate, right? So just make sure you get that distance figured out in there. Now the voltage as well. The voltage is going to be the voltage from one end of the plate to the other plate, right? So that's going to be your change. Is there really like change in voltage? Is going to be from one end. Okay. That being said, here's a bunch of examples here. I'm going to do some examples here in a second, so I'm going to skip those for now. Parallel plate and potential difference. All right, so again, what I'm going to do? We're going to do some examples, I think, and clarify some of that as well. Now, electric forces and gravitational forces. All right, so up until this point, when well, I haven't shown you, but when we did questions like this, we just were able to ignore gravity. So if I've got like two parallel plates, actually, and a lot of times the plates will be like this way, right, where you got a bunch of negatives and maybe a bunch of positives on that side, parallel positives. So there would be electric potential between those plates. So some particle, let's say, was here and then it gets shot over that way. What we were able to do is, because gravity is so much weaker when you think about it compared to the electric force on that thing, we've been able to ignore gravity, right? And the reason why gravity is so much weaker, if you think about it, a very, very small like electron, right? It's the mass on that thing is so very small that the amount of force pulling down that thing is practically nothing. Like, it's so close to zero, it doesn't even matter, right? But the electric force on that electron is actually quite a lot. And when you think about like just that very, very small thing, there's actually quite a bit of a force going on that, right? So the electric force is just so much stronger than the gravitational force is. So usually we can ignore those things, but with very fine experiments, they're actually they're able to do some calculations where you have to take both into account. All right, so when do you take them into account? So number one, anytime you're given the mass of a particle, you should calculate the gravitational force. And if the gravitational force is 1,000 times, if the gravitational force is less than 1,000 times the electrical force, then it's safe to ignore the gravitational force. Right? So if it's not even in the same ballpark, right? Yeah. Number two, anytime a massive particle is suspended or moving vertically in an electric field. So we're going to do some of those in a second, but let's say, positive plates, negative plates, and this thing is like balanced. Well, that would mean that the gravitational force, Fg, was equal to Fe, right? The force, the electric force going up. So then gravity does matter. So that's if it's vertical, right? And then three, anytime a massive particle is accelerating upward or downward. And again, we'll do an example of that too. So, all right. Now, Milliken's oil drop experiment. Okay, we're actually going to talk a lot more about this when we get into particle physics later on. And what this was, there was a guy named J.J. Thomson who was able to figure out the charge to mass ratio of an electron. So that sounds confusing, but all that really means is at the time they were trying to figure out stuff about the electron, like what is it, and they were able to figure out what the charge over the mass was, right? And what that ratio, like a number for an electron was, but they weren't able to figure out what the charge is or what the mass was, right? They couldn't like figure out what had like the bigger percentage of what. So what they needed was an experiment to figure out what the charge of an electron was. So that's what this Milliken's oil drop experiment is. So here's the idea. Here's what he did. So he had, he set up two parallel plates. Okay, so we've got positive on the top, negative on the bottom. So, and then he took what's called an atomizer. All that is like, it's just a spray, like a perfume bottle, right? You like spray it and it would make little oil droplets. And yeah, so there's little oil droplets in there. And those oil droplets, he knew, would have some extra electrons on it. Maybe it would have like 2, maybe it would have like 20, maybe it would have like 50, right? But it would have like some extra even number, well, not even number, but whole number of extra electrons on it, okay? And then what he was able to figure out was, well, if we get those forces to balance, so we get Fe balanced with Fg, then what's going to happen is that you're able to say, okay, well, if the force of gravity pulling down on this oil droplet, so a bunch of, it actually has quite a bit of mass comparatively. So that's all pulling down. So Fg on this oil droplet. And then it's balanced with Fe pulling back up again. And this Fe is coming from the extra electrons that are on this little guy, right? There's like, let's say there was 4 little extra electrons on this thing. Well, those electrons are pulling back up because these electrons are negative. They're going to be attracted to the positives on the top, right? And repelling the other negatives. So it has an electric force going up. So he said, okay, let's balance those guys. So let's get them balanced. He didn't equate like an experiment where he can look through a looking glass, right? And he can wait until they're not moving. So he knows they're balanced. Or he waits until they're moving at a constant velocity. Because remember, if you have a constant velocity, then those particles, the forces are balanced, right? Because it's not accelerating. So they were either stationary or moving at a constant velocity. And then he did some math with it. He said, okay, if Fg is equal to Fe, he knew that Mg, or Fg was equal to Mg, and he knew Fe was equal to the charge times the electric field. And he's able to know the electric field from his experiment. Then he's able to rearrange for Q, right? And he can figure out that Q is equal to Mg times the distance between the plates over the voltage. Oh, sorry, I skipped this part. Your electric field strength was made up of voltage over distance, right? And again, we'll do some examples here. So now, along with these calculations and measurements, Milliken made a number of educated assumptions. So he said that all electrons are identical, so each has the same amount of charge, right? So this is getting into that quantum mechanics stuff where there's a certain charge, and we know what that is now, right? That's that 1.6 times 10 to the negative 19 coulombs, right? That's that elementary charge that we know, but they didn't know that at the time. So he says every one of these electrons, these extra electrons sitting on this oil droplet, has that charge or some charge, right? The mass of each electron is so small that the addition or subtraction of a few will not significantly change the mass of the oil droplet. So he said even if I add 20 more electrons, that's not making any significant change to the mass, okay? The amount of charge on the oil droplet will be a whole number multiple of the charge for that one. Okay, so now, using that, he was able to come up with a value of 1.69 times 10 to the negative 19 coulombs. And we now know that, so he was very close. All right, let's do some practice problem. Everybody ready? All right. A potential difference of 8,000 volts is applied across two vertical parallel plates set 5 millimeters apart. What's the acceleration of a proton placed in the field? What is its final speed if it started at rest? So here's what we got going on. Okay, so we've got, let's say this is the positive side. And this is my negative side. And it says we put a proton in there, so I'm assuming we'll put it on this side. And this thing is going to zip across that way because it's going to repel the positives, be attracted to the negatives. And it's saying, what is the final speed if it started at rest? And what's the acceleration? So we'll find the acceleration first. All right, so here's what we're going to do. So these questions get a little bit funny finding the right equation, right? So let's figure out what we got. So we've got voltage, right? And we've got distance between the plates. And it's asking for acceleration. And I've said a few times, when I'm looking for acceleration, my mind goes to force, right away. And the other reason why my mind goes to force, so force is equal to mass times acceleration, is what I'm thinking. And I'm looking for acceleration. And I actually know the mass, don't I? Because it said a proton. So I know the mass from that. Like I know the mass and I know the charge, right? So I think that's going to be the right idea, is I'm thinking force, right? So then I'm going to look at my equation on my formula sheet. So let's go to the formula sheet. All right, and we're down in this section. Okay, so I'm looking at force, and I'm looking at this one first, and I'm like, no, there's not two charges. I got parallel plates going on, so it's not that one. So I move on to this. Well, there's not even any force in that one, so that's probably not the case in this one either. But looking here, that one looks promising, doesn't it, right? So I've got E, remember this is my electric field strength as well. So I got force on the electron is equal to E times Q. Okay, well, they didn't give me the electric field strength, but I could figure that out pretty easily by using this equation, right? The electric field strength is equal to the voltage over the distance between the plates too, and this was the plates, and I'm dealing with two charged plates. So it's probably a combination of these two guys is what I'm after here. So let's go back and see if we can make sense of this. Okay, so what I'm going to do is I'm going to start with my FE equation and say, okay, force on the electron, or the electric force, I shouldn't say electron, let's do it with capital E, because it's a proton, is equal to the charge times the electric field strength. I'm going to put bars on there because that always kind of reminds me that it's electric field strength. I know that's absolute value, but it just kind of, it can kind of help. Okay, then what we're going to do is I'm going to work my way down. I'm going to say, okay, well, let's start off by doing this. We'll say FE was equal to mass times acceleration, right? So that's the other thing that we can say. We say, okay, I know that force is going to be equal to mass times acceleration, and that is equal to Q times E. Okay, so it's starting to come together right now. All right, well, I don't know the electric field strength, but I could rewrite that. I could just say, okay, well, mass times acceleration is equal to charge times, and then I do have the voltage and the distance between the plates. So let's rewrite that electric field strength as voltage over D. Okay, so now I've got everything. I just need to rearrange, get the mass out of there. So let's say the acceleration is equal to q times v over mass times d. And then plug it all in. So we'll say the acceleration is equal to, the charge in the proton is 1.6 times 10 to the negative 19 coulombs. My voltage, it told me, was 8,000 volts. All over, the mass of a proton is 1.67 times 10 to the negative 27 kilograms. And it told me that it's 5 millimeters apart. Okay, so another way of writing that would be 5 times 10 to the negative 3 meters. Okay, and putting all of that in, we get 1.53 times 10 to the 14 meters per second. That's the acceleration of this proton toward that other plate. Okay, so now it says, what is the final speed if it started at rest? Okay, there's actually two ways to do this, right? Some of you guys might be thinking kinematics right away, right? Because if I knew it started at rest, then that my V1 would be 0. And I'm looking for Vf. I have the distance, right? Because that's the distance between the plates. And I now have the acceleration. So I could use kinematics. But I want to show you could also use energetics here too, right? So I could say, and we do this a lot more, so I'm going to do it this way as well. So finding the final speed, I'm going to say the potential energy before is equal to the kinetic energy after, right? Because at the beginning here, this was all potential to begin with, and it entirely turned into kinetic at the end. So I'm going to say those two guys are equal. Okay, and then EP, I have an equation for that. That's QV, just from your formula sheet. You guys will look for that one again, because I know they get a little confusing now. There's a lot of them. So that's equal to 1/2 mv squared. Rearranging all of that, you get V is equal to the square root of 2q times V over the mass. And for the sake of time, I'm just going to give you guys the answer here. 1.24 times 10 to the 6 meters per second. Okay, number 2. Okay, a proton is placed in an electric field between two parallel plates that are set 6 centimeters apart with a potential difference of 75 volts across the plates. Now, it says how much work is done if the proton is moved 3 centimeters parallel to the plate. So here, just really quickly, if you had these plates set up, let's say those are positive and these are negative, and it says, okay, so this is 6 centimeters apart, and we moved some, what does it say, proton? Yeah, proton. We move that parallel to the plate. So what that means is we're moving it this way, right? So now let's say we moved it over there. This is actually the exact same thing in physics 20, where if you were holding a book at a certain height, and then you start walking, it says how much work did you do? And the answer was 0. That's because I'm not doing any work against the field. The only time work happens would be if I was moving this way or this way. Like the field could be doing work if I was moving this way, and I'm doing work if it's moving that way against the field. Okay, so that's the idea there. So that's 0. So in the first one, it's just 0 because it's parallel to the plate. You're parallel to the field. So, yeah. All right. How much work is done against the electric field if the proton is moved perpendicular to the plates? All right. So in this case now, let's say you've got your object, and then we're moving it this way. So we're moving it up there against, let's say, toward the positive there. So this thing was positive to begin with. I'm moving it toward the positive. It says how much work was done. All right. So, and it says 3 centimeters. So here's the idea, right? I'm going to say, okay, so what do we have for an equation for work? Well, nothing really on that formula sheet, but I do have one like this that says E is equal to Q times V. And really it's change in energy is equal to Q times V, right? Okay, so if we think way back, change in energy is really the work, right? That's what work is. So we really do have an equation for work right now. Work is equal to the charge times the voltage. Okay, well, what's the voltage? It told us that the difference between the plates, right, the potential difference, right, that is voltage, is 75 volts. But that's between the whole plates, right? The plates were 6 centimeters apart. And we only actually moved this thing through 3 centimeters. So really, the idea here, 3 centimeters is half of 6 centimeters. You've really experienced half of the change in voltage, right? So in this case, it's going to be half of this number. But the way we can figure that out, you know, just with the mathematics here, we can say, all right, the change in voltage is equal to, and let's figure out the ratio or like the fraction of the voltage that we have here. So we could say 3 centimeters over 6 centimeters, right? Which is just a half. I'm just setting that up. So times 75 volts is what I'm after. In the end, that's just half, right? That's going to be 37.5 volts. Okay, so now it's not too bad because now we just plug it in, right? So the work is equal to the charge on a proton is 1.6 times 10 to the negative 19 coulombs. And the voltage that it experiences, or the voltage that we move it through, the change in voltage there, is 37.5 volts. So the work done would be 6.0 times 10 to the negative 18. And then remember, we measure work or change in energy in joules. Okay. If the proton is released at the positive plate, what will be the speed when it impacts on the negative plate? All right, so we've done one like this already, right? This is going to be another one of those potential energy is equal to kinetic energy ones. So your potential energy here is the charge of the proton times the voltage. And that's equal to 1/2 mv squared. Now, what's going to change here though? So here, if I rearrange, so here, rearranging this, we get the velocity would be equal to the square root of 2q v over m. But just be careful on this. The only thing that's going to change here is that the voltage here is now going to be 75 volts again, right? Because it's the voltage between one plate and the other, right? Because I'm letting it go out from the positive plate and it's going to the negative plate. So that's the whole voltage that it's experiencing there. So that's going to be 75 volts. And then when you put that in, you're going to get 1.2 times 10 to the 5 meters per second. Okay, Milliken. So we got 2 Milliken ones now. Okay, so number 3 says an oil drop whose mass is that many kilograms accelerates upward at a rate of 2.9 meters per second when placed between 2 horizontal parallel plates that are 3.5 centimeters apart. If the potential difference between the plates is that, how many electrons are on the drop? All right, so very typical question, right? This is it with Milliken. So here's the idea. I always want you guys to draw a free body diagram on these Milliken ones, or really any one where the forces are balanced, right? So what we got going on here, you've got positive plate on the top, you've got negative plate on the bottom. We have the force of gravity pulling down just because of the mass of the oil drop. So we've got Fg. And then you've got Fe pulling up. And notice that I made that one a little bit longer. I meant to, not that much longer. But I made it a little bit longer. And the reason why I made it a little bit longer is because it says that this oil droplet is accelerating upward at 2.9 meters per second squared. So that must mean that there is a net force on this thing, right? It must mean that the electric force is winning. It's winning by a little bit. There's some leftover force there that's causing that acceleration upward. Okay, so that should be enough information there. And I can see, so if that's the case, then this is going to be a net force type of equation that we need to set up. So what I'm going to do is I'm going to say, okay, the net force. So F net, the overall, right, is the net force. That's going to be equal to Fe plus Fg. And, you know, technically these were all vectors. Now, the net force, right, that's the overall force, that's just going to be mass times acceleration, right? This is what we're after, is this acceleration right now, right? Actually, no, sorry. We were given the acceleration. We're not after that. So anyway, that's the acceleration that we were given in this question here, right? Okay, so mass times acceleration. Fe is going to be, well, our equation for that is going to be the charge times the field strength. And then the force of gravity is equal to mass times acceleration, or mass times g for 9.81. Okay, so now technically that was like the vector, you know, that was the vector and that was the vector there. Oh, sorry, not that one. It would have been that one. Okay, so now it matters about our negatives and positives in this, so just be careful. That's usually the place that people will make mistake on these guys. So let's plug in our numbers, but let's make sure we put in the right directions on this. So actually, you know what? Let's not put our numbers in yet. We could probably do that after too. So let's rearrange for Q. So I'll say, yeah, let's do it that way. You could also put your numbers in. I know some of you guys like putting your numbers in, but I want to kind of get used to this too. So what I'm going to do is I'm going to subtract mg from both sides. So I'm going to have mass times acceleration minus mass times gravity is equal to Q times E. Okay, and then just divide that by everything by E there. So we end up with mass times acceleration minus mass times gravity over E. Okay, now we don't actually know the electric field strength though, do we? So, oh, sorry, that was equal to Q. So let's put that in too. So now we're going to have mass times acceleration minus mass times gravity over, and then instead of an E, I'm going to write in what E is equal to, right? The electric field strength is really V over D, and that's equal to Q. Okay, so now when you divide by a fraction, that's the same as multiplying by the reciprocal, right? So that all could just be the same thing as, well, I'll put the D up top. So D times mass times acceleration minus mass times gravity all over V, right? Just really in the end here, I just flipped those two upside down, right? And that's equal to Q. And then nifty little trick we can do here, instead of writing mass twice, I can see that mass is common to both of those. So what I can do is I'm going to factor out the mass. So the simplest way to write this guy now would just be D times, and then factoring out an M, and then A minus G all over V is equal to Q. All right, now let's put our numbers in. So our numbers would be 0.035 meters times 5.7 times 10 to the negative 16 kilograms, just the mass that they gave us for the oil droplet. And then that is times, so I'm going to use square brackets so I don't get confused here, positive 2.9 meters per second squared. That was our acceleration of the oil droplet. And then minus, and then this is where you gotta make sure it's minus negative 9.81 meters per second squared. So that's really gonna become plus. And then it's all of that over 792 volts. And that was all equal to my charge. Keep charging the same side. Okay, so in the end there, we get 3.2 times 10 to the negative 19 coulombs. And that's equal to the charge. Okay, so I did the algebra, like, you know, pretty heavy algebra way there. And again, I want you guys to get used to that because that's really a university skill. They're gonna require that you guys are able to do that. You could have, though, you know, if you wanted to be a little easier on yourself, you could have figured these things out, right? The numbers beforehand, and then did some simple calculations. But you guys have done a lot of ones like that, so I think you'll be all right. But okay, so that's our charge. So now the idea is okay, so this is what the charge was on that oil droplet. And I know that every extra electron on there, right? Every electron has the elementary charge 1.6 times 10 to the negative 19 coulombs, right? Well, if I want to figure out how many electrons there are on there, well, then I have to figure out how many times that goes into that, right? Or how many times I can divide in. So let's do that. So we'll say 3.2 times 10 to the negative 19 coulombs is equal to Q. Oh, sorry. That divided by 1.6 times 10 to the negative 19 coulombs. And we end up getting 2. So there is 2 extra electrons sitting on there. So there would be a charge of 2. And then you write it like this a lot of times, 2e with a little negative symbol. That means electron. So maybe number of electrons would be equal to that. All right. You know what, guys? I'm going to help you set this one up, and I'm not going to do it because it's actually it's the same thing, but a little bit easier. So on number 4 here, we got the same thing. It's a Milliken oil drop experiment, and they're 4 centimeters apart. The student adjusted the potential difference between the plates to be this amount so that one of the drops became stationary. All right, so here's the idea when we do this one. So you'd have your free body diagram, and you'd have FE going up, and you'd have FG going down. And since it's stationary, those 2 arrows are the same length, right? This thing isn't accelerating. It's not accelerating up. It's not accelerating down. Yeah, it's just stationary there. So in that case, right, our F net is equal to FE plus FG formula. It actually gets a little easier because F net, right, that's just 0. There is no net force on this. So 0 is equal to FE plus FG. And another way of saying that is that FE is just equal to negative FG, right? They're the same. You can make those things equal to each other. And then you can just go from there, and it's very similar to the last one, right? So you replace FE with QE, you know, and then replace E with the voltage over the distance, and yeah, go from that one. Couple things to watch out for. I'm not going to finish this one. I think you guys will be all right because, like I said, it's very similar. But a couple things to watch out for here. I don't think I explained that well enough here with the acceleration. So in this case right here, right, our acceleration, it told us that it was 2.9 meters per second squared. So I put that in as positive 2.9 meters per second squared. If the question would have said it accelerates downward at that rate, well, then this would have gone in as negative 2.9 meters per second squared, right? So just be careful on that. That would have been negative if you were accelerating downward. Oh, and the other one was even in this question, right? Even if the word here would have said they were made stationary, if that would have said constant velocity, right? Then I would have handled it the same way, because if this thing was moving at a constant velocity and not accelerating, then the net force is still zero. When things are moving at a constant velocity, they're not accelerating, so there is no force. So just keep those will be the things that'll be a little bit tricky when you guys get doing the questions there. So that should be it. So give that question a try.